Good morning. How are you doing, guys? Well, welcome back, Chapter 5. And today we're going to be covering performance fitness indicators and aerometric. So this is the chapter that's going to be a little bit on the denser side, hopefully not that much. But it's going to be interesting because I'm hoping it would show a little bit about like how we think about when we say this is a good model or a bad model, or why do we even need to qualify these things by saying good, bad, proper, not proper, and such. And of course, I found this quote in Kathy's book, Weapons of Math Destruction, but Francis Cauchy and How to Quantify It. It actually resembles this chapter very well because so say something is good or fair or fine is there is a lot of subjectiveness into it. When you think about the ML pipeline, we're actually somewhere here now. So we've already have a model, and we train this model in our data set. And we have a data set because we have a question and hypothesis that we're trying to analyze. So we built a model, we picked an algorithm, we have a model, and we're trying to evaluate if this model is good or not. So to think about this chapter, the primary goal, as always, in every chapter we have like this big idea, and the big idea we have here is this. How can we declare a model is proper or not? And how can we say that the training process or validation testing process is, works out, and this model now we can trust for this problem, right? So we're gonna have to quantify this. A lot of times when it comes to us, we clearly use qualitative metrics. Saying good or bad or proper is qualitative. What we're trying to do here is we're also trying to quantify it a little bit, like put some numbers into it. Okay, so this is what we're trying to do. So when we think about ML, we know that when we build an algorithm, when we use an algorithm and build a model, we're trying to identify some patterns, and then from the patterns we can predict something, for the most part. And this one tells us or implies that something interesting. This one implies that a good model is one that performs optimally and best describes the phenomenon at hand. Okay, so what does this mean? So perform optimally is one component, and this component says, well, if you really train the model and do any kind of stuff, it should perform optimally. It should give you, predictions quick and accurate. Best describes the phenomena. It tells us that, well, we have some predictions, and these predictions now match the data that we have or the observations we've seen in a very good way. So there is one component on the model itself, and the other one is on the predictions that we get from the model. Now the objective is we need to figure out like a level or like an acceptable level, for instance, here that says, well, okay, well this performance is now optimal, and this description is now good. So we're gonna have to put some labels on these things, and this is where things become a little bit interesting, because whenever we think about CAE, we actually use metrics a lot. You can think always like of regression models. We have R squared or R. If you think about the construction project, on time or like over budget, below budget. Think about air quality, good, bad, air quality index and stuff. So we do have those metrics. It's not something uncommon. However, once you start to think about data, things become a little bit, I don't want to say squishy, but things become a little bit different. Because now the ground truth is data, and we're going to have to figure out a way to, quantify this data. So to start with, let's have this example. And I always find deformations to be like a very unique example because they kind of easy to visualize. You really have a beam and the crest to deform. And in this case, we have, as you can see, we have four data series. The dark one is the actual test, so this is like from a lab with this the beam. And we're trying to build a computer model to replicate this beam because testing beams is expensive as well. So we created three different models, model 1, 2, and 3. And we're trying to see now which one of these three models is actually we feel good about when it comes to replicating the actual beam. The way I like to start this is I try to eliminate things. So we start with the things that are easy to eliminate, and then we go on. And from this case, if we establish, good performance as the model would predict as good as the actual test, when predict the deformation similar to the actual test, then this should be a good model. And by default, by saying that, then model one become worse model. Well, why? Well, visually, it's very far from the actual test. So this is one. And this by itself could be the answer. But what I would like to emphasize is the following. What I would like you to think about now is not just the series is far from the actual test. We're gonna have to say we also have this portion here. So you can clearly see the model has a decaying phase, which we don't see in the test. So despite the model being away from the test, it also doesn't resemble the actuality of it. So if somebody would look at this all the way to here, they would say, well, this is, I mean, the deformation is going up. So we're almost capturing a trend there, right? It's far, but it's capturing the trend. However, beyond this point, the model is hugely different than the actual test. So it's not just the model predictions are far from the test, it's also its behavior. It has a decaying phase, which we don't see in the test. So this is why, for instance, model 3 becomes problematic. I mean, model 1 becomes problematic. You have to take this one out. So coming back, now we have model 2 and models 2 and 3. You can see that it's very easy to witness the green series with model 3 matches with the test better than the red series. So by default, we're going to say, well, model 3 seems to be the best option. But we also have to think about it's not just the closeness of the behavior. Again, it's the closeness of the behavior as well as capturing the actual behavior. If you look at the red series, here the model seems a little bit stiffer than the actual test, and then all of a sudden it becomes a little bit softer than the actual test. We don't really see this peak, that don't see this shift and slope that much. And all of these things together actually pushes model 2 to the side, and we end up with model 3, just because model 3 is the closest one, whether it's value-wise or in behavior-wise. So far, we haven't put any numbers to our discussion. Like we didn't say model 3 is 95% close to model 1, or to the test, or model 1 is like 60% off test. And this is one of the things that we can always have to think about. Well, how do we quantify this? And this is why we have the chapter, trying to quantify stuff. So this is the description of why model 1 is poor. This slide, we go back and we observe models 2 and 3, and we end up with saying, well, model 3 seems to be the good. So if you're a fan of, if you're using finite modeling or publications or papers, you're usually going to have a section that says model validation, which we do something very, very similar to the process. And you're going to say, well, the matching between the model and the test is very close, and hence the model is validated. And then you're going to have to pause, and then you jump into the next section and you start a parametric study. Well, here's why we don't have to jump into that section right away. Because here, somebody would say the following: you know what? Well, what if I had a different, I have a different series? This. purple series. Which one is better, the purple series or model 3? Well, I mean, it's clear that the purple series is very, very close to the test, much more closer than the green series. So somebody would pick the purple one. Actually, many people would pick the purple one. Or what about the green? Some might pick the green, but not as many as the purple one. And here's where we're going to have to say, okay, well, how much the difference is really between model 3 and the purple series? As you can see, the difference is not that far. So close, that bad. In my eyes, both of these are good models, just happen to have that the purple series is a little bit closer to the test. Well, that's not quantification, so we're going to have to quantify the process. What I'm trying to emphasize here is really that you're going to have to try to judge things, not just based on the things you see, but also on the physics behind them, and try to visualize, why do we declare 3 when you could have like a purple series? Well, what if somebody stops at model 3? They don't create a 4th model. Or what if somebody creates 7 models? When do you know when to stop? When is good is good enough? So in this case, we have, of course, qualitative stuff, and we're trying to figure out now a quantitative way or scale to establish this validation. Now, this is not only valid for finite element or for meter models. This is valid for regression models, classification models, ML models, any type of model, empirical models too as well. But this was like a very easy example to set up and see, well, how do we, quantify things? So from an ML perspective, this is why we need, performance fitness indicators. We need a bunch of those, not just one or two. So what I like to go about these is I like to, define them as metrics and indicators. So a metric is usually one thing. An indicator is a collection of metrics together. This is how I like to define them. And these are important because imagine that you build a model and you use improper metrics to qualify the model, and the metrics show you no good accuracy, and you end up using this model, but the metrics you chose are not proper or are not good enough for this model. Or somebody would choose, which we see a lot of this, they would choose 4 or 5 metrics, and they all have high accuracy, and they're going to say, well, we can confidently say that this model works well. However, if you look at the metrics, all of the metrics would be dependent on each other, or like they're just versions or different versions of the same assumptions and problem behind those metrics. So basically, you're using 5 different things, which in reality are just one thing. So we're gonna have to figure out a way to overcome this, and this becomes, with a little practice, a little bit of learning to see what we can do, how can we quantify the different types of models, as well as metrics. So as we said, metrics and indicators. So an indicator is a set of metrics, and a metric is something logical or a mathematical construct, maybe an equation, that tries to measure. This is very important. To measure the closeness of actual values or actual observations or actual data to the observed data. And this could be predicted data from machine learning models, from numerical model from empirical, from different types of. Because usually metrics are general. For instance, we don't really have something that says this is only in a machine learning metric. We have metrics, and the job of a metric is to define how close or how far predictions are from actual values. Now, if you combine a few metrics together, you could have an indicator. Just like everything, all of these have their own assumptions and their own limitations as well. And this becomes important because whenever we say they have their specific assumptions and they have limitations, this is a very good reminder that we need to use more than one. Because whatever assumptions and limitations this metric have or this indicator has, we're going to have to compensate by using other ones that can, overcome these limitations, maybe have better assumptions. And this is why, for instance, this is why this is labeled personally, because this is my personal opinion. I think we need to use multiple ones, maybe somewhere between 3 and 7, However, don't just use 3 and between some metrics blindly. Try to use metrics that are independent of each other. So independent metric. You don't want to use a bunch of them that they all revert back to the same principle. And I'll show you examples in a little bit. And for the sake of this chapter, I do have a slight distinction. So I call these, I have standard metrics and I have functional metrics. So a standard metric is something that you would see a lot in statistics or math. A functional metric is a metric that can quantify the difference with regard to a problem. So it's a little bit more problem specific than the standard metric. So this could be applied as many problems as it. So of course we have regression, we have classification, we start with supervised learning. I think in my slides I only covered supervised learning metrics. In the PDF, which we will see later on, we also cover unsupervised. I just think unsupervised metrics are a little bit too much for undergrads for this short recording. So at the simplest form, a metric is trying to show us, the difference means subtraction between a predicted value and an actual value, or between an actual value and a predicted value. For instance, if the actual value is 3 KSI, this would be strength, and the predicted value is 5, then 3 minus 2 is negative. Now here is the emphasis is on negative 2, which means I'm over-predicting the strength, right? So the negative sign is like a direction. Am I over-predicting or under-predicting? The value itself shows me how much. This could be like one of the simplest metrics. You could also say, well, what can if I don't want to like hassle with the signages, can I just use the absolute values? Of course you can. Of course you can. Oh, well, if you do this, well, you're not dealing with signages anymore, but we can't really figure out what are we over predicting or under predicting. So there's a lot of things that goes with those things. We just have to keep our eyes clear for them. We also have metrics. Somebody would say, well, okay, instead of doing that, can I just use the square? Of course you can. You're going to end up with a square difference. Let's say 3 KSI minus 5 KSI is going to be 2. Square that 4 KSI squared. What's KSI squared? As you can see, everything has its own positives and negatives. Although you're getting away from something, you might be adding something else that you're going to have to figure out how to do. Some metrics are prone to outliers, where metrics are very, very hard to interpret. What does Daisy square is, if you're thinking about days or concentration square. Similarly, you could, maybe have len or log and then all those things. Again, they work out. So we have this paper, it's open access, which means you can access it online for free. And we have about 60, 70 metrics and indicators there. I haven't uploaded, so what I'm doing in the next slides, I'm taking screenshots of the metrics we found in the paper, but I'm not pasting all of them. All of them you'll find in the paper itself, so you can just go to the DOI and find those. In the slides, I'm only having those ones which I think are much more easy to use. Probably you'll use them a lot in CAE, and these are highlighted. So for instance, error is the simplest difference. We have mean error, big difference over the total number of values there. You have mean absolute error. You can see some notes here. Easy to use, works with numerical data, intuitive. So all of these things, RMSE is very common to use. This is good because it's scale dependent. You can have a scale for it. Lower values are usually good. It's still sensitive to outliers because you can have the square. You can have multiple RMSEs for different data, for different subdata within the data set. So everything has, same principles of having those positives and negatives. Of course, R square is very, very common. We like R square because it's easy, negative 1 to 1. R square, if you look at R square and R, they're basically, R square is R multiplied, 2 times. which means these two are highly dependent on each other. So when you see publications or like you see somebody doing analysis and they show you both R and R squared, most likely they're going to follow each other. If R is high, R squared will be high. If R is low, R squared will be even worse, will be lower. So these two are dependent, and we're trying to avoid having dependent metrics. Because instead of showing both, you can just maybe show R squared and then show something else like may or the error or the mean average error, actually that might work out for our case. Yeah, you can see other cases. You also have, reference index, scatter index, performance index, A20 index. All of these are, like for instance, this is an indicator. RMSE plus MAE plus MABE over 3. And it's a very empirical indicator. This one is the same thing. This one is also the same thing. So what these are trying to do, they're trying to combine different metrics and come up with one that tries to minimize the the negatives of the parent indicators and such. So those were for classification. When we think about for regression, when we think about classification, we also have to figure out ways to identify the performance. And as we know, in classification, we're trying to classify or categorize classes. And whenever we deal with classes, we're not dealing with numbers anymore, and then we can't really use R squared and R and all those things. So we're going to have to use different set of metrics. The one that's very, very easy to always remember with classification is what's called confusion matrix. So a confusion matrix is a table, it's a matrix that lists the predictions vertically, the actuals horizontally, and you're going to have here, for instance, this would be, let's say, class 1, this would be class 2, this would be class 1, this would be class 2. And all what we do is we count. We look at the prediction, and we see, is this prediction falling into class 1? If the answer is yes, we hold it, and we see its actual value or actual label. If it's also class 1, then we fit it here. If it's not class 1, then we fit it there, and so on and so forth. So we try to populate this table. And the goal is, we're trying to see, well, how much labels was the model accurately labeling for each class? This is for class 1, this is for class 2. And how many were mislabeled or confused, hence the confusion matrix. So in this case, you can always see that anything diagonally in this diagonal form here, this identifies that how the model is correctly classifying labels. Anything in the other diagonal, this one shows the misclassification or the errors. Naturally, we would like these to be very, very high, and we would like these to. Sometimes you have a different combination of all those things, and all of these are signed. I mean, are indications of how can you fix the model. If you have like too many negatives in one case, well, okay, maybe you have to up the data in that case so the model can see this data a little bit. Remember, main diagonal is the one that correctly classifies the model. We also have many metrics you can put in the same paper. Yeah, one of the main ones is what we call accuracy. We also have sensitivity and specificity. So all of these things are, for instance, if you take this and you sum it to that and you divide by the total number, you're gonna have an indication of how accurate the model is for class 1, for class 2, for all classes together. Accuracy is basically the ratio of the corrected predictions for the total number of stems. So accuracy is a way that we identify how the model works well for all data set. Sensitivity and specificity is specific for the classes. So positive classes or negative classes, and so on and so forth. Which is actually pretty cool. We can break down a lot of things by looking at those metrics. We also have the AUC, or area under the ROC curve. It's a two-dimensional curve. We'll see a picture soon. It basically looks something like and we try to. So the 45 degrees means this is 50% chance that the model works or predicts things correctly. Anything that pushes towards the left corner, that means it's an accurate model. Anything that pushes to the bottom right corner, it means that it's a poor model. Log loss error is also a very good metric. This one penalizes for wrong predictions. All of these are categorical. Yeah, we also have indicators. This is what I call predictivity indicator. We made this one in our lab. So this is accuracy times AUC over LLE. It's a hypothetical indicator with hypothetical values. So for instance, we have the maximum and lowest we can get. I personally like it, but I don't like the fact that it has hypothetical values. So hopefully one day we're gonna sit down and try to figure out a way to improve this indicator a little bit. So everything we discussed before 28 or before slide 28 was standard metrics. These are the ones you see a lot in statistics and math. In this slide coming on, we're gonna now jump into functional and indicators. And remember, functional ones, they serve a function. So it's not just finding out how accurate the model is. They find out how accurate the model is with regard to a certain function or a certain focus. And we have many functions. What I'm going to be spending most of my time on are the ones with energy and domain specific. So these are the two things we're going to have to think about. Energy is actually a very big component because, as you know, when you create machine learning models, they produce or they require a lot of energy, and they end up generating a lot of energy for training, for testing, for validation, for deployment, for saving, for uploading. It's a lot of energy. I think in the PDF we'll see like how much in the number was. Some models they cost millions and millions of dollars. Some models can generate energy that's equivalent to X number of cars, X number of people, a lot of, and we'll see this also, I think, in chapter 9 when we talk about green ML. Green ML is, a subfield of machine learning where we're trying to create energy-friendly, eco-friendly machine learning models. So the goal from functional metrics and indicators is we're really trying to find a balance between accuracy and energy. Because imagine the following, imagine that you have a simple model that doesn't use a lot of energy and its accuracy is maybe 90%. And you have a much more larger complex model that has an accuracy of, I don't know, 93%, but uses a lot of energy. Which one would you use? Would you use the simple model with lower accuracy or the complex model with more energy and higher accuracy, right? So there's going to be a trade-off, and you're going to have to decide for that because we don't really have a way to figure this out. We do have, I think I know why this is not showing. I think that's, there we go, perfect. So let's jump into my browser and see this tool. So we have this tool actually. It's published, so I think there is a lot of work behind it. I think it's great that they were kind enough to allow me to use it in my book. So let's say that you would like to compute how much carbon emissions your GPU. Right? So what we have to do is we come here and we say, okay, well, this is my hardware type. I don't know, let's go with GTX. I'm going to use for 100 hours, let's say 10 hours. And I'm going to be using a specific cloud, a specific region, and I'm going to compute how much energy I'm going to be producing. Well, this is how much energy this particular hardware produces, and this is how much carbon it gets to release. And what I like about this is you can actually publish this. You can take this, you can add it to your latex template, and it actually shows you for this particular code, this is how much energy was created. I think, no, I'll publish it back here. Yeah, so this was a publication from this work. I think there is a few much more papers on the same theme. So you can have that in mind when you start working on your models. Green man, we'll come back to Green man. Somebody would say, well, how do we do this? How do we quantify energy? Well, it's simple. You're gonna have to look at your model, and you're gonna have to say, well, what are the things that I could use that can relate or correlate to energy? And I'm using the term correlation very, very loosely. Well, if you think about model size, if the larger models tend to use a lot of energy. If they train for a long time, they use a lot of energy. If they they take a lot of time to predict inference time, this is a lot of energy, and so on and so forth. And in this case, you'll always see something like this: accuracy over model size, accuracy over training size, accuracy over training energy, accuracy over inference time, inference energy, all those things. I'm keeping accuracy here because it's just easy to link to, but somebody can easily change this into something else, to another metric. Somebody would say specificity, for class A, class B, so on, for over model size. So this one shows us a value, and this value would relate to energy. And of course, this is our own metric. So this is model size, this is training time, and this is prediction time. We came up with this metric because we know that size, training time, inference time is our key indicator metrics. And it's okay, well, if we combine all of these things together, we're going to have a new indicator. And in this case, we have an addition here because both of these are times, so we could easily add them. And in this case, this is model size, so this is usually like in bits or kilobytes. So if you multiply this with this, you're going to end up with something like this, megabit second. And we thought, this would be a way to use it and quantify how much energy we have. There are many other ways that somebody could have done this or even improve. So think about it. My advice is always find something that you're passionate about and try to build on it. So in this slide now we're continuing with functional metrics / indicators, but we're not really focused much on energy. In this case, I'm really focused much on CEE, although this indicator could be used for other things. But in this case, I think this would be helpful to just mention. I know I'm using a lot of beams, and I apologize for that, but I think these are a little bit easier to visualize, at least in my. So imagine that you have a beam, and this beam tries to deflect. So because deflection is a continuous process, you're applying load, the beam deflects, you apply load, beam deflects. So it's a continuous phenomenon. It's not just you're trying to predict trend, or you're trying to predict what air quality or water quality. It's not like yes or no. It continues. And because it continues, we were thinking, well, we're gonna have to, if we're trying to quantify this phenomenon, we really need a metric that's continuous. If you think about R squared, R, all those metrics, they're not really continuous. They show us a single thing. And for something continuous, we thought, okay, we're gonna have to use a metric or an indicator that's a little bit also continuous, so we can try to capture the phenomenon we're trying to figure out. So we came up with a few metrics. Actually, they can all be labeled as indicators, to be honest. We have a few in the book. In the slides, I'm only showing MRD or maximum response deviation because, again, for the sake of this recording, and even my class, I think this was very easy to visualize because the other metrics, the other indicators we had, they had a lot of the structural fire component, and you really need to have like some good basic information about fire engineering before you apply those. But for MRD, it's a little bit easier to visualize. So I'm just leaving this one here. Once you go to the PDF, you'll see the other indicators there. So a maximum response deviation is the following. We have a response. Think of deformation. Think of, I don't know, strain. Think of like a phenomenon that continues. Maybe, let's say, air quality over 5 hours, or air quality over seasons. This would also work out. And I'm trying to find the deviation between the predicted value and the actual value. And my focus in this indicator is on finding the maximum. So you can basically take the same idea and apply the minimum response deviation, or like the average response deviation. Because you have a response, this is a phenomenon, you have a deviation between model and actuality, and you have some form of comparison. In this case, it's the maximum. And this one is very simple. So MRD is you have an observed response at time t. Let's say, I don't know, deformation at time 0 is, or at time 1 minute is 0 mm. The maximum comes from here. I have a maximum observed response. In the test, I've seen the maximum deformation. And this is why for deformations, somebody would go with maximum makes sense because you're looking at the maximum response. If this was a phenomenon that's reversed, then somebody would look at the response. In both cases, somebody could look just at the average. And then I have a largest value of time, let's say 5 hours, 6 hours, 2 hours. And I have a time interval. Let's say I would like to see the MRD every 5 minutes, every 10 minutes, and so on. What's interesting here, and I'm hoping that if you capture this, is this. I have plus and I have minus. And this here plus and minus means I'm calculating this observed response plus the response, the maximum response, and minus the maximum response. So you basically end up with an upper bound and a lower bound, and your response should be somewhere in between, something like this. This would be the test or the ground truth. This would be the ML model, and MRD would be upper bound. So this would be the upper bound, and this would be the lower bound. And as long as model predictions are within the lower bound and upper bound, then at least in my eyes, I'm saying, you know what, for this continuous phenomena, I feel very good about this model. So using the maximum and minimum actually controls this gap. So if you would like the gap, plus the interval, yeah. If you would like the gap to be larger, or if you would like the gap to be smaller, you're gonna have to control it by this portion of the indicator. And we have an example that you can calculate yourself. For instance, if you have the MRD at 1 minute, what the ambient temperature was, 25 degrees, and the maximum temperature I found the test was 500. I'm going with an interval of 10, and so on and so on. Maximum time, maximum interval, maximum observed response. 50 minutes, interval every 10 minutes, maximum temperature I found was 500, and I'm trying to figure out, let's say, the temperature across a beam, temperature across a column, deformation across a beam, the strain across a wall, air quality over time, and like this. And as long as you're within the bounds, then you should be, at least you can feel good about the model. And we have to quantify it. So when we did the simplest form, we said 25%. Less than that is poor. Between that and 50 is fair. Up to 75 is strong performance. More than 75 is an excellent prediction. And all of these, of course, are empirical, which means we've tried a few problems, and based on those, we came up with these limits. I'm imagining these will change with time. Hopefully, once we start to apply more amount, we'll be able to come back and do like much more robust derivation for it. Now, if you remember, what we've done was in standard metrics, we have like a metric or an indicator. Functional, we also have like 1 or 2. Now I'm shifting gears towards techniques. So it's no longer we're looking at the metric or an indicator. We're trying to figure out a methodology or a process to quantify how good we have our models can be. And you can see that we have a few of these. Of course, confidence intervals is a statistical method, and I'm labeling this at the very least because I was really trying to not focus much on statistics as much as I wanted. I wanted to focus on much more of these techniques here, because I feel they're much more like an engineer would relate to these a little bit more than the rest. So for spot analysis, this is how I would like you to think. So it's called spot analysis, which means we're trying to analyze the differences between predictions and actual or ground truth through spots. What does that mean? What does that mean? Well, this means I have something like this. When I went to the lab, I tested a beam, I've tested many beams, and then I'm taking all the deformations and I am organizing the data from lowest to largest. So let's say I have a deformation of 1, deformation of 2 mm, 5 mm, 50 mm, 100 mm. I'm organizing all the deformations I have from low to high. You're going to end up with this ground truth curve, the dark one. You plot it. Most of deformations in beams actually look like this, which is a different story. But that'd be a very good thesis too. And then I build a model, machine learning model, and I've gotten all the predictions I would like, and I'm also plotting these from smallest to largest. So each small one corresponds to its actual value. And you'll see that the predictions will always be something like this. It's a zigzaggy kind of curve. It has a similar trend to the ground truth, but it goes up and down. It goes up and down because the predictions, the model on average from as well. But sometimes it overpredicts, overpredicts. So this is why we have those zigzags. And I'm gonna have to pause and think. And if you think closely, this is what I normally do. Let's zoom in. There we go. So if you zoom in and you look here, you can see, what? A lot of the predictions here are actually not that bad. We're so far so good. All of a sudden, once we hit 80, you see something interesting. You see that we have a lot of the predictions are underestimated. We don't really have the zigzag doesn't cross to the other side of the ground truth. Okay, this is gonna be spot 1. It's gonna be spot 2. This is why it's called spot analysis. You're trying to isolate the behavior into spot, and you're gonna have to analyze these spots by themselves. So what do we do next? Well, here's what we do. This is spot 1. This is spot 2. So if you compare spot 1 and spot 2, you can see in spot 2, we have overall we have a decent behavior. It seems that the predictions are equally across the different portions of the ground truth. In this case, in spot 2, we don't have as good of a behavior. I mean, it's decent because we're predicting, but we don't have as good of as uniform behavior as spot 1. And here's where somebody would say, okay, well, now that I have the spots, let me bring some metric. Let me see R squared for spot 1 and spot 2. Let me get, I don't know, MAE for spot 1 and spot 2. Let me do MRD and see what are the values there. And this becomes now interesting because once you do that and once you look at the numbers, you can easily see something very, very interesting. For something like this, maybe R squared, I don't know, was about, I don't exactly remember how much, but it could be, let's say 90%. If you look here, this would be about maybe 94% or something. This would be something like, I don't know, 80% or 82% or 85%. Which means the following. Overall, your model predicts things nicely, but if you have a beam with smaller deformations, the accuracy of your model is actually high. And if you have beams with lower deformation, your accuracy is a little bit low. Now, why is this important? Well, this is important because beams usually fail at higher deformations. So when you're trying to predict collapse or failure, the accuracy of your model is no longer 90%. It's much less than that. And this is where you're going to have to say, okay, now I have to pause. Because if my goal from building the model is to predict collapse or failure, I'm going to have to up my game a little bit. If the goal from my model is to predict general behavior, or maybe just deformation history up to 80 mm or 100 mm, then I feel good about this model. The other thing that people usually miss is the following. Whenever we measure something in the lab and things tend to collapse, we use touch between the measuring equipment, or say LVDT, and the specimen. And hence it becomes very, very hard to capture those deformations toward failure. Now, the data I'm showing here is actually for beams deformations under fire, which is even worse to measure. It's much more complex to measure things that, under fire condition. So it becomes tricky. And this is why a lot of ML models for fire stuff, we see a lot of this behavior. Because capturing those moments just before collapse is very. If this was like an ambient test, I think we would have been much better. Another technique I like to use, this could be a little bit more intuitive. This is what I call CPC, or case by case. You take your model and you try to predict specific cases or specific specimens. This one, for instance, beam A, beam B. Let's see here, beam A. We have a decent general trend. Overall, we're missing a little bit here. Actually, let me use a different. We're losing a little bit here. Not that, it's about 20 mm. Now this one is actually very cool to because usually I ask this question in my class and I'm going to say, well, what do you guys think about this model? And so that's this here. And most of the students would say, the beam A is much better than beam B. And when you ask about beam B, the question is, well, beam B is missing this much. And it's showing me some negative deformation, which is going to be very, very hard to justify physically. But what about this portion? Well, to me, this portion is actually good. We're capturing the beam much, much better than we're even capturing this portion of this beam. So a case by case could also reveal something, a lot of information about your model. This one says, again, we're also having the same issue with the extreme case where things start to collapse, because you can see the slope here is much, much higher, which means faster collapse. However, for general behavior, before collapse, the model seems to decently work out. Now, if you compare C by C for beams C, D, E, and F, you see that this could be an issue here for some beams, for a very, very small number. And this is where you're gonna have to think, okay, well, maybe I have to go back to my model and see like what kind of small data I have at those small maybe I don't have enough. Maybe I have like some outliers there or something. Maybe some beams were tested, with restraints. So this is why spot by spot becomes a little bit interesting to play with. Yeah, up to 80 mm is good. Whenever we think about, actually, yeah, we could keep this here. So CBC and spot analysis, it reveals a lot on the behavior between global indicators and local indicators. Because globally, you could use one of those standard metrics, and once you start to break it into local portions, you will see the limitations or the challenges within your model. So always keep in mind this. Always keep in mind, well, you don't really always have to look out for the global ones. The global ones are usually easy. The global ones are usually where models perform well. The local ones are the ones that are going to be problematic. I also have, I think, two more techniques. Drawing and stacking is where you take the data set and you take a portion from training, a portion from validation, a portion from testing, and you predict those, and you compare these by themselves. So for instance, if I'm looking at R square for the whole data set, so this is for the full data set. Let me actually zoom in a little bit. You can see that R square is 91. If I take R square for up to 80 mm, it's 85. If I take it up to more than 80%, it's 40. It's a drastic difference. It's almost twice as much. So this is, let's say, this could be in a spot analysis. So R squared for spot analysis for spot, okay, for case A and case B. Then if you start to say, well, what if I take 50%, if 50 just randomly 50% of points, how much R squared would be for everything that I have? Well, 91.9. What if I take 50% and another 50% random? Well, 91.4. And you can always see that these two are going to be close to that, to R squared, because you're taking 50% of the whole data set, right? Now, what the difference would be, somebody would say, well, can I take, 25% of testing and 30% of validation and the rest from training? You could do that, of course, because the goal is to try to investigate your model as much as randomly or deliberately, because this helps us with the model. It's not really, we have to understand how the model behaves. Rational vetting is one that's actually was added to the bar, I think, in the third draft. It wasn't there in the first one. I was debating for a while, but then I think it's good to have. So let's think about this for a minute. Let's say we have a model, and the model has, I don't know, 3 features: time, load, boundary conditions. Again, it's a view. So at time 0, we shouldn't have any deformations, right? Because we don't have any load. So if you plug into your model at time equals 0, t equals 0, the model should only predict deformation of 0. There's nothing going on. If the model predicts 5 mm or 15 mm or like negative 3 mm or 40 mm, then you're going to have an issue. This is what rational vetting is. And this clearly shows the issue with data-driven analysis, because the model doesn't understand the physics. The model doesn't know what the relationship between load, time, and boundary. In physics-informed model or causal models, this rational issue doesn't become a big item, because the model takes into account the actual relationship. Black box models, explainable models without physics, actually may fall victim to this. So it's also good to go back to your model and try to see if it can predict physical things that can actually happen. For instance, if you have a loading of -2, what kind of deformation you think you're going to have? You ask your model and see if that matches physics or not. So this is one way about rational vetting. Of course, there is a lot of other techniques too. Confidence interval is there, but it's purely a statistical method. So I try to tell you we have a confidence interval that you can have. However, I would rather we focus on the other ones, like physics ones or something like this, where we're gonna have to have a lot of the engineering component that we need to. Now give me a sec. I'll be back with my video. Okay, perfect. We'll come back. So let's see what we have here in the PDF. So the main goal, as we all know by now, is we're trying to figure out what are fitness indicators, error metrics, why do we need them, how can we judge our models. So all of these things are discussed. We've seen this example. We know what metrics are. Oh yeah, this For instance, here R and R squared are related and hence dependent on my thought processes. Maybe try to use independent metrics. Yeah, here's what I was trying to show. So you can find these. Where's rotation? Here we go. You can find all of these metrics, like in the paper I've listed in my slides. This is just like a very long list of metrics. I don't think you need all of them. Maybe just have 5 or 6 handy. Yeah, I've seen, for instance, some metrics I've seen like in special publications. Like for instance, if you have like a lot of fluid and stuff, so you have the citations there. If you're doing anything with hydrology, you may refer to the publications. And go back. Yeah. Oh, yeah, clustering. So for unsupervised learning, we have a few indicators, like for instance, elbow method, coefficients. We have some indices. No, this is the other one. Let me just check this. Hopefully, Um, I was actually hoping to have all of these metrics in, yeah, this is like ROC curve, different types. Frequencies, distances. Yeah, these are the ones for unsupervised learning. You could glance through these if elbow method is visual. For instance, you would see the number of clusters, because if you remember from previous chapter, we don't know how many clusters do we have. So once you start to plot, let's say the weighted errors and stuff, and you can have a curve like this with the number of clusters. Once you have like a distinct point that shows, okay, this might be like an elbow, and hence this would be the the optimal number of clusters. Of course, there are other ways to identify the number of clusters. This is just was one of them. Yeah, we've seen this. Yeah, okay, so this is the one I've actually wanted to discuss. I know we touched upon this in the slides. Let's say we have model A with 96% accuracy, consumes 50% more energy than model B, accuracy 94. Now, both models are designed to do something. In this case, let's say average vehicles passing through intersection at 1 hour. For a problem like this, the small difference in accuracy is small, 96 and 94. But the difference in energy, 50% is large. So why would you, I mean, I always think about this. Do we have a good justification for using model A, which uses more energy than model B, while both have decent, good accuracy? I don't know. But somebody would say, well, this may not be like a very fair way to compare these models because we have many, many more things to look at for, different than other than accuracy and energy. What about size? What about training? What about data? All those things. Well, I think that's a good point, but I think I try to simplify things. And when it comes to, let's say, accuracy and energy, something like very basic like this, I think my intuition would say, let's try the accuracy for 94% and see how it works. Perhaps the additional 2% of accuracy in model A may not warrant. It may not warrant something. Maybe somebody could go back to model B and tune it better and make it a little better, or go back to model A and try to tune it such that it doesn't use as much energy as it uses now. So all of these things, they have a lot of philosophical perspective into them, and I appreciate like if you have any thoughts on those to share with me. Yeah, for instance, in Beacon 74, citation 78 and 74, they found, I think that they reported that there is a deep learning model has the potential to generate over 20,000 to 80,000 kilograms of carbon emission. One American car produces 16K kilogram of emission annually. So this is many, many cars. This is how complicated or how energy consuming developing models can be. But yes. So here where I touch upon other domain specific indicators, we have Clemson metric and we have CCM metric. You don't see these in the slides. They're a little bit they require a lot of like background information on fire stuff, fire engineering. But the idea is really simple. These are classification metric. And in fire design, structural fire design, you look at a column and you would say, well, I need the column to last for 4 hours or 3 hours, 2 hours. So you give it like a time. Fire is called fire resistance rating. And because it's an hour, it's the dominant will always have 60, and this is as a minute, 60 minutes. So the goal is to see the fire resistance rating predicted. You subtract the ground truth and you divide by 60, you can get like the number, the accuracy that you need. And then you take CM and you get in the CCM, get them overall accuracy for the whole model in terms of fire. So this is very specific fire resistance. If there are other phenomena where, let's say, it's time specific, and instead of 60, maybe you can use, I don't know, every 30 minutes or instead of even time, you can use distance every 30 kilogram. Yeah. kilometers or every 30 miles or every 30 concentration of something. I don't know. These also could be modified for those things as well. So MRD, we've seen MRD. This is another example of an MRD. I know it doesn't say it here, but this is actually the deformation or the axial deformation of columns with time under fire condition, specifically concrete filled steel. They have a structural fire is a fascinating topic. Whenever you have a column that's restrained and you have heat, you can have an expansion phase, and then once the material starts to degrade, you can have a decaying phase, and then things contract and it's collapse eventually. This is why the deformation curve for, let's say, of structural elements under fire conditions is something very important, because it's like the DNA of the behavior. If you can capture that, that'd be good. We've done spot analysis. Yeah, this is like I don't like when, but I didn't like when some methods would say, well, here's like a 5% error or 10% error. I didn't like the arbitrary bound that's given, like, why 5%? Why? I wanted something a little bit more dynamic, and hence we ended up with MRD. But even MRD, if you really want to like look at its inception, we don't have standard time interval. Well, I guess this is the only thing. Go back and double check. Yeah, this is the only thing that you can actually control, because this one here, you see this in the test. You also see this in the test. So these two things that you can't really control. You also see this in the test. This is the only one that you get to select. And in fire, usually we go with 5 minutes most of the time, sometimes 10 minutes. Sometimes they might go for like 30 minutes or an hour or so. But I just felt that using something that we know from domain knowledge, let's say 5 or 10 minutes, carries a little bit more weight than saying 5. Just the arbitrariness of having 5 and 10% was a little bit, I was questioning it for a while. It works for many domains, though, don't get me wrong. But in my case, at least for my problems, it was a little bit different. We've seen those. We don't really have much left. Yeah, this is why we have a star, if you remember my discussion. Yeah, this might be a good thing to do. I know we talked about deformation before, but another example would be the following. Let's say you have an element and you have cracking if you heat it. So if in your model you add like 0 centigrades for heating effect, but the model still shows you cracking, then we're gonna have a problem, because cracking is a function of heat. So this is one way to have, rational fitting as well. Conclusions. Yeah, we know what these are. Definitions, we know what they are. Advanced techniques, yeah, covered all those questions. Let me see, do we have something interesting? Yeah, 5.6 is usually a good homework. Problem. Yeah, here is actually where Mo and Abrash helped me a lot with this. So we collected all these metrics and we had them like in Python packages and R codes and stuff. So if you want to use one of these metrics, we have them all listed out here. And you could also use Excel. So Excel sometimes can be a little bit tough for some unique metrics that we need to find out. So these are a lot of those metrics that we use. That's it for this chapter. I'll see you soon for the next chapter. Well, if you have any questions, just let me know. Hopefully this was interesting. As always, be safe and stay in touch.